Good evening. Good evening. You're welcome to our tutorial today. In our last class in chemistry, we treated the kinetic theory of matter, and we moved to the kinetic theory of gas, and we introduced the gas laws. So today, I think that day we discussed the Boyle's law, right? Boyle's law, and we did a calculation on Boyle's law. So today, we'll continue from where we stopped. Today, we'll continue from where we stopped. So I'm trying to explain gas and Boyle's law. We said that Boyle's law talks about the variation of the volume with pressure, right? At constant what? At constant what? Temperature. So how volume of a gas varies with its pressure at constant what? Temperature. And we use the jar fitted with a piston. We say, okay, that if you move down, remember what we said about the compressibility of gases, right? Hope you can remember that gases can easily be what? Compressed. So if you have a container like this, a container that's just small amount of gas here, before what's going on, it will do what? Spread and fill the entire container. So you go to that now, you can easily, if you fit a piston here, you can easily do what? Compress it. Two of us compress it. But you cannot do that easily with liquid, let alone solid. Because they look for a way to escape. Trying to force it down, you may break or you may bulge out. Two of us. Yes. So now, what happens here? We use this. I'm trying to do a recap of what we discussed on Boyle's law. How we use kinetic theory to explain what Boyle's law. And I say that actually that if you, as you can see here now, this, let's assume that this is the first volume occupied by this gas. Okay, the first volume occupied by this gas is what? V1. If you want to get V2, you either move the piston this up, you get the what? V2, or you do what? Move it down, you get the what? V2. So this is V1, and you move it up, If you move it up now, you are increasing the volume, right? The volume will do what? Increase, right? And the pressure here is reduced. Are you aware? Now the pressure here is what? Reduced. As you increase the volume by pulling it up, the pressure will do what? Reduced. Now, but if you, because the number of collision on the walls has decreased. Trophies. Now, but if you push down this piston, push it down, you have changed the volume from V1 to V2. But this V2 now is a decrease in volume. Trophies. It's a decrease in volume. But for you to be able to decrease this volume, you need to apply. You push it down. Now here now, this small volume here, the pressure here will be more. Because the number of collision here will be more. True of us?
True.
Good. So the volume has decreased, but the pressure has done what? Increased. So that's why this is kinetic theory explanation of Boyle's law. That's why Boyle's law at constant was there heat applied here? No heat applied. So the temperature is constant. You didn't change the temperature. It's only the pressure and the volume that will vary altogether. So that's why Boyle's law states that the pressure volume is inversely proportional to what? The pressure at constant what? Temperature. So this, are you with us? Are you sure? I don't think we are aliens, or this topic is alien to us. At least we know one or two things there. Alright, so this is exactly what we mean by kinetic, using kinetic theory to explain what Boyle's law. This is basically what we did in our last class. Okay. So having taken note of that, we move to another law. We move to what? Another law. This is the law by a French scientist, Charles. Popularly known as what? Charles law. Charles law. So let's move to Charles law. Help me with that, please. Thank you. So according to Charles, the volume of a given mass of a gas, is directly proportional to its temperature in Kelvin, provided that the pressure remains what? Constant. Sorry, our reference book for today is New School Chemistry for Senior Secondary School by Oseyo Ababio, as revised by L.E.S. Apanisi and Herbert Igwe, 2016 edition. And Prefective Chemistry, UTME past question. These are our reference books for today. Most of the things we said today will come from them. All right, now let's move forward. So this is what Charles law states. Charles law states that what? That the volume of the given mass of a gas is directly proportional to its what? Temperature in what? Kelvin. Provided that the what? Pressure remains what? Constant. Actually, that's what this man did. What this man observed. The man actually observed, and this number I'm about to say now will lead us to absolute temperature, what the concept of absolute temperature, and why we convert from degrees Celsius to Kelvin before calculation. Actually, the man observed that at 0 degrees Celsius, that the volume, he observed that the volume of a gas, of a given mass of a gas, will increase by 1/273 of its volume. That the volume of a given mass of the gas will increase by 1/273 of its volume. Will increase by 1/273 of its original volume at 0 degrees Celsius for every 1 degree rise or fall in what? Temperature. He observed that you have a gas, a given mass of a gas that has, say the volume is 273. Let's assume that the volume is what? 273. The volume is what? 273 what? CMP. Let us know that this is the volume of this gas. Now, it says that for every 1 degree, can you see the board? For every 1 degree Celsius rise in temperature, for every 1 degree Celsius rise in temperature, that the volume of this gas will increase by 1/273 of its volume. Are we together? Now, let's do the calculation. This is the initial volume, right? And let's assume we have just 1 degree rising, 1 degree rise in temperature, 1 degree rise in temperature. This will increase by 1/273 of this volume. So what do you mean that 1/273 of 273 is what? Is 1 cm cube, right? Is 1 cm cube, right? Simply do 1/273 times what? 273 over what? 1, which is simply what? Are we together? Are we together? So what this means that 1 degree rise in temperature, the volume of this will increase by what? 1 cm cube. So that means the volume will change from 273 to what? 270 what? 4. True or false? True or false? Look at it critically. 273 to what? 270 to what? 270 what? 4. But let's assume that in this case now, let's assume that it's a decrease. So if there's a decrease in 1 degree fall in temperature, 1 degree Celsius fall in temperature, 1 degree fall. So what will be the final volume? If it has 1 degree fall in temperature, the volume will change by what? 1 over what? We decrease by 1/273 of this volume. So if there's 1 degree fall, so this will still be what? 1 cm cube, right? So it will fall by 1 what? Cm cube. That means the volume will now become what? 270 what? 270 what? 272, right? Good. Now, I'm trying to explain something here. Now, from the work of this man now let's now assume that what it means is that if the volume, if the temperature keep falling, if the temperature keep falling to the extent that you have up to 273 degrees Celsius fall in temperature, what will happen? If you have 273, that means this 1 cm cube, because 1 degree will fall by 1 cm cube, right? So if you have 273 degrees fall in temperature, that means it will fall by what? 273 what? Cm cube. That means the volume of the gas will do what? Disappear. The gas will have no volume again, true of us. But in recess, this does not happen. In recess, this cannot do what? Happen practically. Theoretically, the volume will become 0, but it's not possible. That means the gas will do what? Disappear. But it's not possible. Now, this led to what we now see today as what? Even though this is not feasible practically, but it has some applications in the calculation of what? The behavior of gases. Now, this led to what we call what? The absolute what? The absolute what? 0. Are we together? Are we together? Now, this absolute 0 now, by implication, at that 0 degree, at that 0, what is it? What it implies is that the remember we are talking about 4 now, right? 4. If it's 4, it will have -1 degree. True of course. 4 by 2, we have -2, right? So if it's 4 to 273, we have minus what? Minus what? 273 what? Degrees what? Celsius. minus 273 degrees Celsius. This is what? The absolute what? Absolute what? The absolute zero what? Temperature. Are we together? Because here at this point now, the Kelvin scale starts here. Are we together? Known as what? 0 Kelvin. That's why today you start seeing something like, if you want to convert, if you want to convert 0 degrees Celsius to what? Kelvin, and if you want to convert Kelvin to what? Degrees Celsius, what do you do here? From what you know so far? You add what here? You add what here? 273. Now if you add 273 here now, it will give you what? 0 Kelvin. Are we together? If you add 273, it will give you what? 0 what? Kelvin. Now, this is that temperature at which the volume becomes absolute what? Absolute what? 0. Am I completing? Even though practically the gas will not be what? Disappear. But here now, at this point now, the temperature of Celsius, of degrees Celsius, stop here. Why that of the Kelvin start from here? From here, out together. No, based on this now, because of this issue now, before you can do any calculation using or that has to do with temperature in these gases, you have to convert this movie to what? Kelvin what? Temperature. Because it's not feasible for this at this point now to start having. If you are working with this down, that if you are saying that the gas will do what? Disappear. Am I complicating? Here now, this adding 273 takes care of this. Here now we start from 0 Kelvin and start to do what? Going up. Start from 0 Kelvin and start doing what? Going up. Even though this degrees Celsius, for degrees Celsius, it starts at what? 0 degrees what? Celsius. Am I complicating? No. So if you now want to do what? If you want to, before you any calculation that has to do with this temperature, move it from what? Degrees Celsius to what? Kelvin. By simply adding what? 273. Add to 3 here, it becomes what? 0. Am I complicating? So this is what? The absolute temperature. The absolute. That's why today the Kelvin scale is rated as what? The absolute what? Temperature. True of us. The absolute what? Temperature. I just decided to explain one or two things here so you understand why you convert this from what? Degrees Celsius to what? Kelvin. Instead of using the degrees Celsius and doing your what? Calculation when it comes to gases. Because of this behavior. Are we together? Now, so now with this, let me now go to mathematical aspect of this Charles law. Let me go to the mathematical aspect. Remember your variation in your mathematics, right? Remember your direct variation. If you remember your variation is your separate mathematics variation, then you can relate with this Charles law. Charles law is a direct what? Variation. Because here the volume varies directly proportional to what? The temperature. Are we together? At constant what? Pressure. So the pressure is constant while the volume varies directly proportional to the what? Temperature. Now, so with this now, if V is the volume, if V is the volumes and the T, capital T is temperature in Kelvin, not in Kelvin, while P is the pressure, which is constant. That means that the volume is directly proportional to what? Temperature, T, at constant what? P. Are we together? Good. The volume is directly proportional to what? The temperature at constant what? Pressure. Now, if that is the case, we can now say confidently that we need for us to have, this is just an expression of proportionality. For us to make it, what was that? I think I told you silence this phone. So why is it making noise again? Okay, now that the volume is directly proportional to what? The temperature. Now, this is just an expression showing proportionality. Okay. Now we need to move this to be an equation. That means we need to remove this sign of proportionality by introducing a what? Constant. Okay? We can, by introducing a constant, k, or whatever you choose to use. So if you introduce a constant, k, v now becomes what? Equal to what? K what? T. V now becomes what? Equal to what? Kt. So if you make k the subject of the formula, k is now equal to what? V over what? T. Volume over what? Temperature. What it means is that at any point in time, if you get the volume at this point divided by temperature at the same point, it will give you a constant value. Get the volume at another point divided by temperature at that point, it will keep giving you the same value. That's the meaning. Remember, in absolute temperature scale, absolute temperature is not degree Celsius, is what? In Kelvin. Very important. Don't just take the law without mentioning that Kelvin. Very important. Kelvin. Very important. So that your gas will not disappear. I hope together. Yes. Because the gas will not disappear. If you follow it like this, now at this point the gas will disappear. Which is not true practically. Okay? Now, so the K is equal to what? V over T. Now, if at point 1, that is V1 over V2, if V1 over T1 is equal to K, V2 over T2 is equal to K, V3 over T3 is equal to K, what it means is that V1, V2 over T1 will always be equal to what? V2 over T2, which is also equal to what? V3 over what? T3, and so on and so forth. That is the implication. Who is confused there? Can you see the board? Good. Okay, let me explain. Now, look at the board. But you got from it to the right? Good. I'm trying to explain the meaning of this constant here. What it means is that, let's assume, because we are talking about variation, change in volume with regard to change in time. Sorry, temperature. So if you see things like V1 over T1, V2 over T2, what it means is that the volume, this is the first volume. If the volume changes to this volume, what will temperature, if the temperature changes from here to here, the volume will also change from V1 to what? V2. So this means this K, this constant being equal to V over T means that V1 over T1 will give you what? K. And V2 over T2 will also give you what? K. And V3 over what? T3 will also give you what? K. If you like, you can say K1, but K is constant, it's something. That's the meaning. So by implication, if V1 to V2, V1 T1 will give you K, V2 T2 will give you K, V3 T3 will also give you K. What it means is that V1, this matter than another T1. What it means is that V1 over T1 is equal to what? V2 over what? Which is equal to what? V3 over what? Pump up to what? Vn over what? Tn. Do you not understand this? And this n means any number. This can be 200, V200, if there's anything like that, over T200 to infinity. So V1, T1 will always be equal to what? V2, T2. So to make it simple, you now choose only the first proportion. V1, T1 is equal to V2, T2. This is how Charles law. It's not a Charles law you'll be using in solving in your calculation of gas law. So this is how this equation came about. So V1, Charles law said that V1, unlike Boyle's law that said that V1 is equal to what? V2. Charles law said that V1 over T1 is equal to V2 over T2. Is it clear? Is it clear? Now, that's a Charles law for you. Now, If I ask you to convert Celsius temperature, the following Celsius temperature to Kelvin temperature, that one is easy now. 148 degrees Celsius to Kelvin, what is it? You add what? 273. It's easy, right? If I ask you to convert 2125 Kelvin to degrees Celsius, what it is? To convert 125 Kelvin to degrees Celsius, what it is? You said 273 minus, is it 273 minus the degrees Celsius or degrees Celsius minus 273? Which one?
Degrees Celsius. Kelvin transfer from Kelvin to degrees Celsius.
It's what?
Kelvin minus.
Say it now. Yes, no, say it now.
It's already in Kelvin. I don't know how to change it.
And you say you know. Say what it is.
Kelvin minus degrees Celsius.
If you're, what are you saying, sir?
You said one. Repeat the question.
We are moving from Kelvin to degrees Celsius. We are saying Kelvin minus degrees Celsius. We are moving from Kelvin to degrees Celsius. What are you going to do? China, tell us. Tell us what are you going to do?
Like moving from what to what?
Kelvin to degrees Celsius.
Kelvin to degrees
Celsius or Celsius, anyone,
you might not like from the Kelvin, might not
good. So we subtract 273 from the Kelvin and get your degrees Celsius. Simple.
273 minus that.
You are still saying you're still repeating the same mistake you made in the first place. You are saying 273 minus Kelvin. What are you saying? I say if you convert Kelvin to degrees Celsius, is what?
You said something now.
Something what?
You said something now.
I say that we should convert how to convert Kelvin to, I say 125 Kelvin. Convert it to degrees Celsius. Say, repeat what you said now.
Like, you from that Kelvin, that name, you might not 273.
Good. But you are saying 273 minus Kelvin. Okay, we are going to do 125 minus Kelvin.
That gets minus something.
Hey. Okay, if you solve, yes, minus. If you do 125 Kelvin minus 273 is minus, then you're right. Do you understand it now? If you want to move from Kelvin to degrees Celsius, simply subtract 273 from that Kelvin given and get your answer in degrees Celsius. Whether it's minus or whatever, make sure that you put the sign. But if you are moving from, in fact, let me give you some, since this I thought this thing is a walkover, but since it may give issues, let me give you something to solve before we move to, because you need this thing in this gas law. Okay? So let's do it. Let me write answer from this textbook and see how far we can. You solve it now. I'll give you just a few minutes. You solve it and tell me the answers. So in moving, let's work on moving the Kelvin from degrees Celsius to Kelvin. Let's work on moving from degrees Celsius to Kelvin. So let's convert the following. Let's convert the following. Okay, number one is 148 degrees Celsius. Number two is 0 degrees Celsius. Number three is minus 132 degrees Celsius. Let's move these things to Kelvin scale. This is degrees Celsius. This is Kelvin. So you tell me your answers fast. Which are 4 to 1? Okay, you added 273. Is it correct? Is it correct? Who disagree with that? Do you all agree with that? Have you solved it? Who has solved it?
It's correct.
It's correct. Alright, 4 to 1 what? Okay. Okay, what of degrees Celsius? Yeah, 273 what? It's not degree Kelvin. Please, Kelvin has no degree. It's not degree Kelvin. Just Kelvin. Okay, out of -132 degrees Celsius. Any opposing answer is what? Just add 273 to -1 times 2. You have what? 1 watt, 41 watt Kelvin. 141 Kelvin. All right, let's look at. Let me give you another thing on to solve on how to converting from Kelvin temperature to Celsius temperature. Can I clean this now? All right. From Kelvin temperature to Celsius temperature. Let's do that one and see what we get. We have 125 Kelvin. We have 405 Kelvin. We have 298 Kelvin. Oh yeah. You said? 1 watt. Which one? Okay, 125 Kelvin is 1 watt. 148 watt. Tell me the answer now. -148 degrees Celsius. Any opposing answer? Huh? Any opposing answer? Huh? Okay. I'll give you like 2 minutes. So yeah, solve all the questions and tell me the answer. I'll see I'll check your work and see what you are doing. Bridget, you're welcome. Thank you for following up. Crypto Divakiti, welcome. Olusegun Bello, welcome. Alpha, who has finished? Okay. What is it? Okay, all right. So let's look at. We have a lot to do today. Please let us not waste our time here. All right. Okay, 125 is what? Simply do what? 125 minus what? Minus what? So what's the answer? Minus what? 140 what? 48 what degrees Celsius. This one is what? Okay, simply do what? 405 minus what? Minus what? So what's the answer? 132 degrees what? Celsius. What of this one? 298. Simply do 298 minus what? What's the answer? 25 degrees room temperature, right? At 0 degrees, in Celsius scale is 25, but in Kelvin scale is 298 Kelvin room temperature. Are we together? So this one is easy, right? Now, so with this now, I think we can move and see. Okay, but before we do that, I want to explain Charles' law using kinetic theory of matter. The same way I explain Boyle's law using kinetic theory of matter. It will help you to understand it. Now, let's also use the container fitted with what? fitted with what? Piston, okay? But this time around you hit it. You will do what? You hit. Okay. Now, let's assume you have this container, right? Containing gas, okay? And inside it we have what is it called? Piston, okay? Okay? That can move up and do what? Go down, okay? Can move up and do what? Go down. Now inside here is the what? The gas. All together. Inside here is the gas. Initial with an initial volume what? V1. Okay? V1, initial volume V1. Then and at the temperature what? T1, okay? The volume is V1, temperature is also what? T1. Now, you will heat it. Remember what we say about the relationship between kinetic energy and the average kinetic energy of the gas molecules and what? Temperature. That temperature is a measure of the average kinetic energy of the what? The gas molecule. Remember? And remember what we said about heating it. If you apply heat is a form of energy, right? Right? If you apply heat, what happens is that this heat energy you apply here, energy is not lost. Energy is transformed from one point to what? From one form to what? And a law of conservation. Remember the law of conservation of what? Energy. This heat energy you apply here will be converted to what? Kinetic energy, which is also mechanical to true of us. Now the particles of this gas, the molecules of this gas, this gas molecule now, they are just there on their normal energy level. But once you apply heat, they will gain this heat energy you apply as kinetic energy. And their kinetic energy will do what? Increase. True of us. Their average kinetic energy will do what? Increase. And the collision, the collision, the number of collision of these particles will increase. True of us. Because they now have more what? Energy. So because of this more energy that they are acquired through this heat, the collision per unit area. Remember pressure is force per unit what? Area. Remember, and collision is a type of force per unit area. The number of collision per unit area will do what? Increase. And if it increases, that means the pressure will increase. Now, if this thing moves up, if this thing moves up, it will normalize this, it will move up. Even if this thing move up, it will maintain the number of collision per unit what? Area. Even as more heat is being applied, they gain more kinetic energy and more collision is as the number of collision is increasing. This thing moving up will counterbalance it, okay? Maintaining the same number of what? Collision per unit what? Area. As the more heat is entering, this one is moving on, it will keep maintaining that number of what? Collision. But if this is constant, not moving, the pressure will be what? Increasing. The pressure will be what? Increasing, because this thing is not moving. Am I completing? So you can actually intentionally. That's why also there's also pressure law. Have you heard of pressure law? We say that the temperature is direct proportional to what? Pressure. When the volume is constant. If you want to witness it, if you maintain this volume constant, if you don't move this volume, if you keep it constant, and as you are hitting, the pressure will do what? Will be what? Increasing, because the volume is constant. The pressure will be what? Increasing. All together. But because you are moving, the volume is increasing, the pressure is maintained what? Constant. Okay? So now, this explains Charles' law. To keep this pressure constant, the volume will what? Increasing. While the heat, you apply more heat. So temperature is increasing and the volume is increasing at constant what? Pressure. But if you want to get if you want to explain pressure law, you keep this volume constant, maintain this piston at this point what? Pressure. So that's why, according to pressure law, at constant volume, the temperature is directly proportional to what? The pressure is directly proportional to what? The temperature. So, the temperature is increasing, the pressure is also what? Increasing at constant what? Volume. Are we together? Are we together? Are we together? So, this is kinetic theory trying to explain Charles' law. I have explained Charles' law and pressure law. So, I don't think I'll go into that again. Pressure law says that the volume, the pressure, at constant volume, pressure is very important to what? Temperature. Okay?
What about the graph?
The graph of what?
Charles' law.
Charles' law. It's a direct variation now. What is so difficult there? Direct.
How do we do that?
It's actually depending. If you are using a Kelvin scale, anyway, I think it's okay. The question is not completely wrong, okay? If what is here, if this is volume, right, and this is temperature, if what is here is degrees Celsius, remember, if what is here is degrees Celsius, here is 0, here is positive 2 what? 73. Okay, out there, and here is minus what? 270. If what is here is degrees Celsius, you see something like this. Okay, but if what is here is what? Kelvin, you just simply see. But remember, we are dealing with Kelvin, right? You simply see. Just know that direct is like this. Direct goes like this. Because like this one is increasing. This one is also what? But for Boyle's law, inverse goes like this. Okay? Okay? Like this. It slopes down. It slopes down. Inverse. Direct goes like this. Okay? And then thank you for that question. I like that. I assume that is what you should know by now. But this is not SS1 class, it's the jump class, right? But it's okay across the what? Like this. And we are here in common as what? 273 degrees Celsius. Here is what? 0 degrees Celsius. And here is what? 273 degrees what? Celsius, as the case may be. Are we together? Is it clear? So this is how kinetic theory explains Charles' law. And by extension, I talked about pressure law, even though I don't think it's in this table. But you know about the law, right? So that I explained about keeping the volume constant. That's what happens in pressure law. That's why you see things like this. That P1 over T1 is equal to what? P2 over what? T2. Are we together? Good. So it's a direct variation. Now, STP, a certain mass of gas. I think let me write this on the board, so we can be looking at it so that our audience that will be interested can solve on their own. One week on Mariana. Okay, now let me write to the board. It's better than calling it. Okay. This question is from New School Chemistry, page 86. The example is there. Example 1 says, Alright. The question says, at STP, a certain mass of gas occupies a volume of 790 cm3. Find the temperature at which the gas occupies 1000 cm3 and has a pressure of 726 millimeter mercury. Before you can solve this question, there's something. Okay, wait. There's something that enters this question. Wait. All together, just wait. Let me talk about the general gas equation, okay? Before we can look at this question, okay? I've talked about Charles' law, Boyle's law, pressure, right? Then now let me now talk about the general gas equation. Now look up. Boyle's law says that volume is inversely proportional to what? To what? Pressure, right?
Yeah.
Right? At constant what? Temperature. This is Boyle's law. Charles said that the volume is directly proportional to what? Temperature. At constant what? Pressure. So with this, we can combine this. This is a direct inverse variation. This is a direct variation. So we can combine these two to get a joint variation. Actually, general gas equation is a joint variation. It's a joint way. You know variation. You have variation in mathematics, right? That general gas equation is actually a joint variation. Now, inverse variation, direct variation. If you combine the two of them, you get a what? Joint variation. Now look up. Let me combine the two of them to get general gas equation. Because sometimes you're given the volume, pressure, and temperature of gas. That's what you see here. That's why I want to talk about it before we continue. Now, so if you have a situation like this, so how do you now combine this? This is direct inverse, and this is inversely proportional to this, and this the same volume is also what? Directly proportional to what? This thing. So you simply pick. Since we have V here, you pick one V, okay? Proportional to what? Over 1 over what? P. Dot what? Dot what? T. All together. This dot is multiplication. All together. So if that is the case now, this will become this and this is what? T over what? P. So the same V is direct proportional to T. The same V is inversely proportional to what? P. So if you want to remove the sign of proportionality, you introduce a constant and put equal sign to make it an equation. So this, remember we're talking about general gas equation, not general gas expression or general gas proportionality. No, it's equation. So to make this equation, this becomes volume is now equal to what? K what? T over what? P. KT over what? P. So if you make this K the subject of this formula, you get something like this. That K is now equal to what? Of course, you go multiply, right? If you cross multiply, you have that K is now equal to what? What? V over what? Over what? T. Is it, who is lost here? Please, if you are lost here, please talk. Who is lost here? Tell me so I can explain more. Can you see the board? Okay, we are on the same page. We are all on the same page. So if K is equal to PV over T, by implication, what it means is that at any point you multiply P. If you multiply P1 by V1 and divide by T1 is K. If you multiply P2 by V2 and divide by T2, to give you what? K. If you multiply P3 by V3 and divide by T3, it will still give you what? K. Multiply P4 by V4 divided by what? T4 will still give you what? K. Multiply blah 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 to T Pn times Vn over Tn, it will still give you what? K. So if all of them will still give you K, what it implies is that If P1 V1 over T1 will give you K, P2 V2 over T2 will give you K, P3 V3 over what? P3 will give you K. That means Pn Vn over what? Tn will also give you what? K. By implication, P1 V1 over what? T1 is equal to what? P2 V2 over what? T2, which is equal to what? P3 V3 over T what? 3, which is equal to what? P1 Pn Vn over what? Tn. That's the meaning. So you can just take the first two, and this first two gives what our general gas what? Equation. Are we together? So this first two gives us our what? General gas equation. So if you are done putting it down, I'll give you like 2 minutes to solve this question yourself. Let me see how far we can go.
That's STP.
Talk now.
I remember the grade is 7 watts.
Don't worry, we'll get there, don't worry.
We have to use it as well.
Huh?
We have to use it as well.
It depends. Okay. That means before I can solve the question, there are more concepts I'll talk about. It's okay. Finish one first. So the question will stay. I don't put it down. Now let me explain standard temperature and pressure, STP, before we can solve this question, okay? Now let me explain STP. Correctly? Yes. All right. This question is bringing up a lot of things. But it's okay, at least we'll not discuss it again. We go over to other things. Okay, now let's talk about standard temperature and pressure, STP. Standard temperature and what? Pressure. Now, basically, you know the temperature, the weather, climatic condition and weather and water, the climate condition differ from one part of the world to another. Nigeria, this part of the world is tropical, is hot than those in UK, other parts of the world that are temperate. Am I communicating? In fact, as we are suffering from heat here, there are some people that are cold and clean somewhere. All together. As our water here, our normal water we see is liquid. You just take it and drink, take it and bathe, take it like that and cook. There are people, the normal water they see is what? Solid, ice block, snow. That's normal water they see. If they want the liquid water we see everywhere, they will go and do what? Boil it. True of us. They will melt it first. True of us. Before they can see the liquid water we see under normal circumstances. And we here, before we can get their own solid water, we go and put it in the fridge. True of us to get. So because of these differences, you can measure something there. You can take some volume of a gas or whatever, and if you come back here, it will change. So that leads to have a uniformity, a standard at which a measurement can be done. Say that this is what it is at this temperature, at standard temperature. That what led to what? This standard temperature and what? Pressure. Am I communicating? Now, so when you talk about this, the standard temperature and pressure as follows. Now, for pressure is what? It can be in Newton, it can be in different units, it can be in millimeter watts. Mercury. It can be in Newton per watt, meter watt square. This is pressure. You do it for what? Pressure. So in meter mercury is what? 760. You know what the yes is? Is what? 760 millimeter watts mercury. But the SI unit, that is Newton per meter square, is what? 1.01 times 10 to the power 5 Newton per meter square. You can put it down. In Newton per meter square, the standard pressure in Newton per meter square, and that Newton per meter square is actually the SI unit. In Newton per meter square is what? 1.01 times 10 to the power 5. So, temperature, uncle, what do you think about pressure? Temperature? 270, right? In Kelvin, right? So, I'll give you 2 minutes to solve this question. It seems 2 minutes is too much, so I'll give you 1 minute. How many minutes? In German, a question should be around 40 seconds or so. I think it was initially 45. I think it's around 40 seconds. Alright? So but I'll give you 1 minute to solve this question. Alright? Don't call it after that.
The figures are much now.
Anyway, it's not a jam model question anyway. It's not jam, it's not modeled. You know that jam, the way they set their question, you don't need a calculator. You don't actually need a calculator to solve jam question because you don't need it.
What they gave us this time.
You don't need it. You don't need it. Standard jam question, calculation. You don't need calculator.
Question like this.
Okay, like this one, but not this one. You don't need. Even this one, say I don't think. Alright, so I give you 1 minute. Let me see your answer fast. Can I not know?
Our first pressure is that 60 hours.
So what's the answer? Solve and give me the answer. Oh, yeah, are you done? Are you done? I gave you a question. You asked me a question and a question I gave you. Solve your question first. When you are done, then I am out. 1 minute, please. 30 seconds gone. Peaceful peace. Welcome. 45 seconds gone. Let me write down the second question while we wait. Is that what's important? Who else has finished? After this, we'll start solving questions. After solving all these questions, if they are set that, we'll move to past question. In our next class, we'll enter Dalton's law of partial pressure. In our next class, we'll enter Dalton's law of partial pressure. Are you done? Are you serious? No, it's not true. Let me see what you did. Let me see it. So what? Okay, no, let me solve this. All right, look up. The question says, look up, just pause, look up. The question says at STP, a certain mass of gas occupies a volume of 790 degrees Celsius, 790 cm3 at STP, a standard temperature and pressure. The volume is what? 790. Find the temperature at which the gas occupies 1000 cm3 and has a pressure of what? 726. You can decide that if you like, you can call this STP, the standard temperature and pressure, T1, P1. Anyway, you can call them T1, P1. Okay, so you can call them T2, P2. It doesn't matter. But what matters is that if you are calling them T1, P1, that means this volume should be what? V1. If you decide to call them T2, P2, this volume should also be what? V2. You cannot call the standard temperature and pressure T1, P1 and call this volume V2. You will fail it. And you cannot call the standard STP T2, P2 and call this volume V1. You will fail it. Are we together? So now remember the general gas equation says that what? P1 V1 over what? P2 over T2 is equal to what? P2 V2 over what? T2. This is T1, sorry. This is general gas what? Equation. Solution. Okay? Okay? Now if that is the case now, P1 if you decide that the standard pressure will be what? 1. Will be designated with 1. That means P1 is equal to what? 7 what? 7 what? 60 pressure now. Standard pressure is what? 760 millimeter mercury. Because this one is in millimeter mercury, you can leave it in what? Millimeter what? Mercury. But if this one was in Newton per meter square, you go to what? Use 1.01 times 10⁵ what? Newton per meter square. Remember that the standard pressure in Newton per meter square is what? 1.01 times 10⁵ Newton per meter square. In millimeter mercury is what? 760. I said it here now, right? Did you put it down when I was saying it?
You see, it can be this thing or that.
Depending. Let's assume that this question came here and used pressure that has the unit Newton per meter square. The standard pressure you use here will not be in what? Millimeter mercury. It will be in what? Newton per meter square, which is what? 1.0 times 10⁵ Newton per meter square. Are we together? Now, so here, P1 is what? 760 what? Millimeter mercury. V1 is this volume. Remember they say at STP the volume is what? 790. So the volume should be what? 790 cm3. Why the standard temperature is what? 273 watts Kelvin. We are done with 1. Let's move over to 2. P2 is what? 726 millimeter mercury. Then V1 is what? 1 is what? Then the people say find the temperature at which the gas occupies 1000 cm3 and has a pressure of what? 726 millimeter mercury. So that is the temperature we are looking for. Is it not? So we make that from this general gas equation, we make T2 the subject of the formula. If we cross multiply and make T2 the subject of the formula, T2 becomes what? P2 V2 times what? T1 over what? P1 V1. So we have what? P2 V2 times what? T1 over what? P1 V1. So we'll start substituting these values here. We'll start doing what? Substituting these values here. So if we start substituting these values, then we will have what? 760 millimeter mercury. Sorry, 7 what? 26, right? P2 is what? P2 is what? 726 millimeter mercury times V2 is what? 1000 cm cube times T1 is what? 273 Kelvin over what? P1 is what? 760 millimeter mercury times V1 is what? V1 is what? 790 cm cube. So let's cancel out the units. Millimeter mercury will do what? Cancel millimeter mercury, right? CM cube will do what? Cancel CM cube. We are left with this. So yeah, but you can punch a calculator if you want. What's the answer? Another person should punch a calculator. Use a calculator. What's the answer? Just simply multiply 726 by 1000 by 273 and divide by 760 and 790. What's the answer? What's the answer? What's the What's going on? Is that how can this move, man? How can this move? Oh man. What is the Kwaka? Yeah. What's the answer? 3 what? 330 point what? Good, that's the answer. 330.1 what? 1 what? 1 what? 1 Kelvin, right? 330.1 Kelvin. That is the what? It's okay, it's okay. 330.1 Kelvin. It's okay. That's the answer, okay? It's good. That's the answer. This is not difficult. It's very, very simple. Okay. Now let's look at another question. Okay, are you done with this? Can I clean? Okay, you're sick of me. Fast. We have barely 5 minutes to go. Please, I want us to solve as many questions as possible before we go. I want us to solve as many questions as possible before we go. Baby, welcome. Fast, so I can write another question. I can clean here, right? This side. All right. Okay. Let's look at this question. Okay. Let's look at this question. It says a given mass of a gas occupies 850 cm cube at 320 Kelvin and 0.92 times 10 to the power 5 Newton per meter squared pressure. Calculate the volume of the gas at STP. I solve. I'll give you 2 minutes to solve this one. Two minutes. Baby, welcome. Richie, welcome. Please feel free to drop your answers on the comment section. Feel free. Jenna, welcome. Okay. 1 minute gone. Amy, welcome. One minute, 30 seconds gone. You know what matters here is your speed and your accuracy. So you should be fast so as to be able to attempt as many questions as possible, and at the same time be accurate in what you are solving. Very important. I think 2 minutes. And the last. How far? Who has finished? So what did you get? 660 point what? 660.53. 660.53. Okay. Somebody got 660.53. Let me see if any of the audience was able to get anything. Okay, let's solve this. Solution. Let's solve it. No time to waste. Let's solve it. Solution. Okay? Let's solve the solution. Only one person got 660.53 watts CMQ. So let's see whether the person is correct or not. Okay, as usual, you have your the mass, that the mass is fixed, that one is constant. So let's look at, before you know the law you're going to use or you push you're going to use, please look at the parameters given, okay? So if you look at this question, you have volume there, volume is there. You have temperature is there, and pressure. So volume, temperature, and pressure is there. So this we tell you that you use what general gas equation to solve this. So P1 V1 over T1 is equal to what? P2 V2 over what? T2. So from this question, what is P1? From this question, what is P1? The question says a given mass of the gas occupies 850 cm3 at 320 Kelvin and 0.92 times 10 to the power 5 Newton per meter squared. So the P1 is 0.92 times, are we following? The P1 is what? 0.92 times 10 to the power what? 5 Newton per meter what? Squared. Are we together? While V1 is equal to what? 850 watts CMQ. Then T1 is equal to what? 320 Kelvin. 320 watts Kelvin. Now, P2 from the next stage now will take us to the what? Standard temperature and what? Pressure. Because we are asked to calculate the volume at standard temperature and what? Pressure. So P2 is the standard pressure. But remember that the P1 is given in Newton per meter square. So if P1 is given in Newton per meter square, that means the standard pressure should be in Newton per meter square. And the Newton per meter square is what? 1.01 times 10 to the power what? 5 Newton per what? Meter square. Are we together? Now, so V2 is what we are looking for, question mark. Then T2, the standard temperature is what? 2 watts, 273 watts Kelvin. 273 Kelvin. We are looking for V2. So in this general gas equation, we make V2 the subject of the formula. So to achieve that, we'll go back to the equation. So V2 from the equation is equal to what? V2 is equal to what? P1 V1 times what? T2. P1 V1 T what? 2. All over what? P2. Well, this is what I'm looking for. So P2 T1. P2 what? T1. And from the values listed, we'll start substituting these values for each of these. So from the value given, P1 is what? 0.92 times 10 to the power what? 5 Newton per meter what? Square. Times V1 is what? 850 cm3. 850 cm3. Times T1 is what? 320 Kelvin. Divided by what?
No, it's T2.
Have I made a mistake? Yeah, thank you for the correction. So here should be what? 2 watts. This shows that it's possible that you know this thing and still enter exam hall and fail it confidently and go home. You know it too. So please be careful, okay? You see how I just interchanged this whole thing. So be careful in solving. Are we together? So here should be what? 2 watts, 73 watts, Kelvin over what? P2 is what? 1.01 times 10 to the power what? 5 Newton per meter what? Square. Times T1 is what? Is what? 320 Kelvin. So let's cancel the units. Kelvin will do what? Cancel Kelvin. Newton per meter square will do what? Cancel Newton per meter square. So what you are looking for is volume. That's why we have our C2 remaining. So just deal with numbers. Multiply 0.92 times 10 to the power 5 by 850 by 273 divided by 1.01 times 10 to the power 5 times 320 and get your answer. You get your answer in CMQ. Fast. Okay, Jonas, one of the one of the they say that the answer is 659 cm3. So someone got 659 cm squared. That should be cm3, not cm squared. 659 cm3. So what's the answer? What's the answer? Alpha. So what did he get? Okay, someone got 0.54. How did he did what? Someone got 6 here on the online. Eh?
He did this thing before the final answer, so that was.
Okay, he approximated what?
He approximated at the.
Where?
When you did it,
Punch it, let me see your own fast. I'm just allowing because this is what if you go to Ray jam question. Nobody should use calculator because jam question you don't need calculator in jam question. You don't need calculator. You can solve it with that calculator. We know what number then. Oh yeah, do let me see what they are doing. $60.5 $60.53. Okay. It's okay. Okay, 60.53. What do you get? Is not the calculator is not calculator yet. Let me go see what to do here. Okay. Alright, so I think we've spent enough time on this question and we've not solved anything from past question. We have like 18 minutes to go. So the answer is actually what? What's the answer? The answer is just 60.5. You got it. And how far? What did you get? One of us online got 659. Maybe that was this or something. The answer is what? 660 point what? That's 60.53, but you know that this is CMQ. It shouldn't be a what? 2 decimal places, okay? 1 and 2 decimal places is okay. 6.5, you can discard that one. And I leave that 60.5 CMQ is okay. 60.5 what? At least you should practically in your integration. You can never get, you cannot measure CMQ in 2 decimal places. 1 is okay, if at all. 1 is okay. So that's why I can leave it at 60.5 instead of 60.53 or 54. Okay. So this is the answer. 60.5 cm. Okay. Now let's at this junction now. Okay. There's one more question I want us to solve now. After that, we go to jump question and see what we can make out from the report. Can I clean here? Can I? Good. Okay, the question says, But we have 1 minute to solve this question. 1 minute. This one shouldn't take you time. 1 minute to solve this question. 1 minute. 1 minute. Thirty seconds gone. What's the answer? 160 point what? 160.8 cm cube. So one person got 160.8 cm cube. Once we enter jump questions, no more calculator.
No.
I told you. No more calculator. Solve it without using anything. Once you enter jump question, after this now we enter the jump question. No calculator. Because you don't need it. For 5 seconds gone. Let me see if somebody has solved it here. Okay, I have 161 cm cube. So much approximation, 161 cm cube. This journal avoids so much approximation. Okay, who else? What did you get? Anyway, it's not bad anyway. It's not bad. Anyway, it's not bad. 161 is not bad. It's not bad anyway. Who else? Jude Alpha. Yeah, you have not gotten anything correctly. What? I have really. I'm not heard anything from you. Are you sure? Alpha, Fancy. How's it going? Afiaro. Confusing. Let me see what. No, which law are you using to solve this thing? Which one are you using? Look at the. Well, remember I told you that if you see any question, try to look at the parameters given. It will give you a guide on the one to use. Look at that the question. What are the parameters given in the question? Every question.
161.
Correct. Look at the question. What parameters are given there? Volume and what?
Okay.
The question says at 17 degrees Celsius. 17 degrees Celsius is what? What parameter is that? Temperature. It's not temperature. Now, a sample of hydrogen gas occupies 125 cm. 125 cm is what parameter? Volume. What will be the volume at 100 degrees Celsius? The same temperature. If the pressure is constant. So what law are you going to use to solve this question? Answer. Tell me. Just mention the law first. Whose law? Is it Charles' law? Is it Charles' law? Correct. So if you know it's Charles, then go to that, go get them the business and tell us the answer fast. So if it's Charles' law, then go use Charles' law and tell us the answer. First, look at the question, study the question and know the one to use. Don't jump and start using anything you see. You make mistakes. Okay? Nancy, I'm waiting for you. Use just now. Where do you end that just now? Begin to end it at B1 over D1 No, you do. I didn't see B1. What are you looking for? Now make the video with the sort of color from right now. Problem now. Okay, you were not there at the beginning of the class when I said that if you are giving, when I talked about this issue of the volume disappearing, to avoid that anything they gives you, once it deals with this, you don't omit it like that. You can leave that when you want. But this one is a good fact. Okay? But if you leave it like this, it's not wrong. Am I communicating? But sometimes some questions that will have OBJ option, you will see once it's one. Are we together? But the one that I will completely say no is if you start telling me that you have 160.84 CMP, I won't take it from you. Okay? Are we together? Even though, yes, practically it's not possible. Okay, practically. So what did you get? You try to get the phone, right? Are we together? So we have gotten the answer, right? Going to solve it again. Let me solve it for our audience. Past solution. Alright, now look at this. Let's look at this. Semantic align it with what you did. Using Charles' law. This has temperature, volume, and pressure constant. So you will use what? Charles' law. V1 over what? T1 is equal to what? V2 over what? T2. Are we together? So, but we from the question now, we have our V1 to be what? To be what? 125 what? cm3. Our T8 what? 290, right? We have 290 Kelvin. We have 290 what? Kelvin. Then V2 is what we're looking for, right? You don't know it. It's equal question mark. Then T2 is equal to what? 100 degrees Celsius. We move it to what? Kelvin. So we add what? 273. The answer is what? 373 watts Kelvin. Are we together? So, excuse me. Alright, so sorry for the. So you add 273 here is what? 373 Kelvin, right? So with this now we can now make V2 the subject of the formula. So V2 is now equal to what? V1 what? T2, alright? Over what? T1. Hope I'm correct. Huh? So with this now we can find the V2. So V2 is now equal to what? V1 is what? 125 cm cube times T2. T2 is what? 373 Kelvin over T1 is what? Kelvin. So Kelvin will cancel Kelvin. So you cancel out. What's the answer? 160.8. It's okay. You can leave it at 161. It's still not bad. Okay. Right. So that's the answer. I've gotten the answer, right? Okay. So now let's pick one question from. I will use this photo to show you that JAMB doesn't require a calculator. You see that it's suffering yourself, trying to get up and down. Let me. I will say. I'll give you the question. Then give you the options. You now see the reason why it's that you don't need a calculator. Once you see that question, look up. So this question is from JAMB 1999. Chemistry, question 5. 1999 chemistry, Question what? 5. Jam 1999 chemistry question 5. The question says, let me write on the board. Hope you are still alive. Okay. The question says, this is JAM 1999 chemistry. Question 5. It says, what is the temperature of a given mass of a gas initially 0 degrees Celsius and 9 atmosphere? I didn't mention that pressure also measured in what? Atmosphere, okay? Atmosphere pressure. It can be in millimeter mercury, it can be in Newton per meter square. It can also be it can also be in atmosphere, okay? Measured in atmosphere.
That's pure.
I said the pressure can also be measured in atmosphere. The unit can also be. You said puberty.
I said what's the formula? Is it purity?
Look at this. Tell me from there and solve. I'll give you 1 minute to solve this question first. I want you to try it yourself. Okay? Before I can tell you the answer or how to solve it, try it yourself first. It's very important to do it yourself first. It boosts confidence first. Am I committed? That's why I want to do it yourself first. That's why I want you to do it yourself first. Seconds gone. Did you touch a record? Why? No, why did you touch a record?
I wanted to touch calculator and then I use my head.
This is how JAM question is. JAM, you don't need calculator in JAM question. I keep saying this, people find it difficult to understand this. You don't need it. Because the options, they will select numbers that you don't need to, start borrowing yourself. But the issue is that you have power over numbers. Can you handle numbers? That is the question now. Some people, once they see number, they become afraid. So what you got? What did you get? For 12 seconds gone.
I'm afraid. Stop.
You are afraid of what? Of what?
The numbers.
And who else? Someone got, let me see if there's any answer from the audience. Okay, none. Someone got, what did you get? 91 Kelvin. Who else? Our 1 minute is gone. Let's solve it so we can go. Let's solve it so we can go. We have tried for today. Remember I said, the first thing to do is to look at the question. Look at the parameters in the question. That will inform you the law to use. In today's class, we touched Boyle's law a bit. We described Charles' law, ideal gas equation or general gas equation, and pressure law. Now look at the question. The question says, what is the temperature of a given mass of a gas initially 0 degrees Celsius and 9 atmosphere if the pressure is reduced to 3 atmospheres at constant volume? Now let's bring out the parameters in this question. What is the temperature of a given mass of a gas initially at 0 degrees Celsius? This is temperature, right? So the parameter there is what? The first one is temperature. And the 9 atmosphere. Atmosphere is pressure. Pressure is there. If the pressure is states the variation of temperature with respect to pressure at constant volume. Which law? Pressure law. And if you bring up in pressure law, the pressure is directly proportional to what? Temperature, right? So simply put that P1 over T1 is equal to what? P2 over what? T2 at constant volume. And you are good to go. So P1 from this question is what? P1 is what? Let me come here. From this question, P1 is what? 9. Tell me, P1 is what? 9 atmosphere, right? 9 atmosphere. Then T1 is what? 273. T1 is what? 0 degrees Celsius, right? We move it to what? Kelvin. 0 plus what? 273, which is what? 273 what? Kelvin. Then P2 is what? 3 atmosphere, right? Yes. 3 atmosphere. Then the second temperature is what we are looking for. True or false? So we make T2 the subject of the formula. Here, this implies that T2 is now equal to what? P1 T1, right? P2 T1. Are you following? P2 T1 over what? P1. So let's multiply. P2 is what? From here, P2 is what? 3 atmosphere. Times T1 is what? 273 watts Kelvin. Over P1 is what? 9 atmosphere. So let's cancel out the unit first. Atmosphere, we'll cancel atmosphere. We are left with what? Kelvin. 3 will go here, right? 3 divided 9 is 3. 3 divided 273 is what? 3 divided 27 is what? 9. 3 divided 3 is what? 1. The other is what? 91 Kelvin. Porsche can get on here. So this is doing it on jump. Is for you to know how to play around numbers. Once you can play around numbers, you are good to go. It's simple. So the answer is what? 91 Kelvin. The answer is 8. 91 Kelvin. I think we should stop here. We are losing light.
I have a question.
Ask. Yeah, ask.
So I bet define that pressure law for me.
No, pressure state that at constant volume, that the pressure of a gas is constant volume, yes, is directly proportional to the temperature in Kelvin. Simple.
At constant
Volume. The pressure of a gas is directly proportional to the what? To the what? Pressure. Or simply say pressure of a gas is that proportional to what? Temperature. But it's when the temperature increases, the pressure will do what? Increase. Put it like this, it's better like this. At constant volume, the pressure of a gas is directly proportional to what? Its temperature at air. In Kelvin. Are we together? That's what pressure law states. It will also follow all those things we did, that P in T. Look up. If look up now, it also follows that P is that proportional to what? T. And P is what? KT. And K is what? P over what? T. And P1 over T1 is equal to what? P2 over what? T2. Simple. Are we together? Any other question? Right, in the absence of any question, we'll stop here for today. Tomorrow, okay, because of I clean what I wrote, sorry. Should I write it again? This is B1. Please, someone should help out. Please, put this in down, please. We have some changes because of the change in the menu, okay? Please, look up. I know that most of you will not have it that side.
Something, I don't do it.
These two movies will not happen. You're just going to need to come. Alright, please look up. Our time is 4 to what? 4 to what? 6 p.m. Then Monday, Tuesday, nothing here Wednesday, okay? Then Thursday, Friday and what? Saturday alone, okay? Monday is biology. Tuesday is chemistry. Thursday is English language. Friday is physics. And Saturday is mathematics. Okay? Saturday is what? Mathematics. 4 to 6 p.m. That's how the timetable will be from now henceforth. Okay? Alright, thank you very much for your attention. I also want to thank the audience for your contribution. Be here with us every Monday, Tuesday, Thursday, Friday, and Saturday, 4 to 6 p.m. Other days, Wednesday and Sundays, as the when necessary, I'll also be live for other courses. See you next time. God bless you.